Hello and welcome to CSE 373, Section 3, Recurrence, Party, and Hashing. In this section, we'll be doing some recurrence analysis review, some work with the master theorem, as well as an introduction to hashing. For course announcements, the only upcoming deadline is, the only immediate deadline is exercise 2, which is due on Monday, 4/16, with a late due date of Thursday, 4/19. So feel free to use any late days if you have to. We gave you 2 weeks to complete P2. So please start early. This is legitimately 2 weeks of work. So don't try and do nothing for the first week and then try to cram it all into the second week. In my opinion, this is a more complex project than P1. And this is due Wednesday, April 26th, with a hard deadline of Saturday, April 29th. Jumping into recurrence analysis review. Remember, a recurrence is an expression that lets us express the runtime of a recursive function. And the recurrence is split up into 2 cases. The first one is the base case. So this top line, base case, where we do a constant amount of work when n takes on certain values. In this case, 0 and 1 will trigger the base case for this recurrence. The second case of a recurrence is the recursive case, and that's this bottom line here, RC for recursive case. The recursive case is split up into 2 terms, where this first term is the constant, or not constant, it's the amount of work that we do in a recursive case, and then the rest of the work will be done by future recursive calls, which we represent by some sort of recurrence with a decreasing n value. Here's what I just said, where t of some decreasing n value will be our recursive call. We're going to walk through problems 1a and 1.3a together. And for problem 1a, an identity called Gauss's identity will be very helpful to us. If you have the worksheet pulled up, there are a bunch of formulas and identities on the very last few pages of your worksheet. So make sure to have those available for reference. For Gauss's identity though, basically what it's saying is if we have some sum from I is equal to 0 to some value minus 1 of I, then this will simplify to that top value, well I guess plus 1, times n minus 1 over 2. And we're going to use this to solve a recurrence later on. And then we should use our answer from 1a to get 3a more quickly. We're going to plug our answer from 1a into our answer for 3a when solving 3a. All right, walking through 1a, finding bounds, we have to analyze the runtime for this block of code, where we kind of have 3 sections here. We have an outer loop that will run n times, as the blurb says. We have an inner loop, that will run I times, because it depends on the outer loop value. And then in the very center of these nested loops, we have some constant amount of work. Let's say that we're doing 1 operation here, though you can definitely make an argument that we're doing 2 for result plus plus, right? We're doing an addition where we're adding 1 result, and then assigning the result of that addition into result. But because, again, we're doing asymptotic analysis, the difference between a plus 1 constant work and a plus 2 constant work doesn't really matter in the long run. We can write these operations where the outer loop runs from 0 to n minus 1, the inner loop runs from 0 to I minus 1, and the inter loop does some constant amount of work as the summation. Let's break the summation apart. This inner term is the constant amount of work we do for every iteration of the inner loop. Constant work this inner sigma or summation is the inner loop. It's like saying, for an instance of an inner loop, how many times do we loop? Well, we go from 0, or j is equal to 0, to j is equal to I minus 1. And we do this constant amount of work for every iteration of this inner loop. So the total amount of work the inner loop will do is 1 plus 1 plus 1 plus 1, etc., all the way until j is equal to I minus 1. And then it'll stop when j is equal to I. Finally, this outer summation, as you can probably guess, is our outer loop. What the outer loop does is it will sum the runtimes of each instance of our nested loop for all the values from I is equal to 0 to I is equal to capital N minus 1. So constant work, and then we sum all that constant loop, the amount of constant work we do for each instance of the inner loop. Then we sum all the inner loop work via these outer loop summation. And we can simplify this and get it down to something we can actually use using Gauss's identity. To start, this is an identity on your cheat sheet, but the sum from j is equal to 0 to I minus 1 of 1 is equal to 1 plus 1, sorry for the poorly drawn ones, etc., plus 1. And we sum 1 I times from j is equal to 0 to I minus 1. What's 1 plus 1 plus 1 I times? Well, it's the same thing as multiplying 1 by I, or just I. So that's why we can simplify this inner summation to I and end up with this sum. Does this sum look familiar? Well, this is a summation from I is equal to 0 to some value minus 1 of I. This is exactly Gauss's identity. So we can use Gauss's identity to simplify the summation to capital N times capital N minus 1 over 2. And that's how we end up with this runtime. Now, let's use this runtime to solve 3a. Oh, and here's the actual bounds. We can simplify our n times n minus 1 divided by 2 into 1/2 n squared minus 1/2 n. And then using our asymptotic analysis rule of dropping lower order terms and removing constants, we end up with big theta or big O of n squared for this chunk of code. All right, next up is problem 3a. So 3a is, given this function, write and solve a recurrence. First off, whenever we're trying to identify the runtime of a recursive method, we should probably break this apart into the base and recursive case. Well, the base case is right here, where we're doing a conditional check and we're returning 0 if that check passes, or if capital N is less than or equal to 1. So here we're doing a constant amount of work, constant work. And let's say that there's one operation occurring here. Again, there are actually two operations, but because we're working with asymptotic analysis, it really doesn't matter in the long run. Next up, let's identify our base case, or our recursive case. Well, this is exactly problem 1a, from this line to this line. We already found the runtime for this chunk of code, which was capital N times capital N minus 1 divided by 2. Okay, and the only thing that's different is in the recursive case is that we have this last return line. In order to write a recurrence, we're going to need to identify how many recursive calls we're doing, as well as how much we're decreasing the input for each recursive call. Well, looking at this, we make 1, 2, 3, 4 recursive calls, and in each recursive call, we're dividing the input by 2. We're also doing a constant amount of work here, but again, we're going to drop this in our final recurrence, because on this line, all that really matters are the recursive calls. and we're already doing n squared work, right? If we split a recurrence into the work recursive calls do, and the rest of the work our recursive call does, or the current call we're doing, the current call we're on does, then we would break it apart into we're doing n squared work here, and then we're doing one work or constant work here. The n squared work will dominate the constant term, so we can leave it out of our recurrence. Cool. This is everything we just went through. And note that the base case only happens if capital N is less than or equal to 1. And this is the recurrence we talked about, where we're doing one or constant work for the base case, or let's just write it as 1. We have our 1a term here from part 1a, or n squared work. And then for recurrences, we made 4 recursive calls, and each recursive call we divided the input by 2. Now, this is a form of a recurrence where we can apply the master theorem to solve this recurrence and find the big theta runtime of this recurrence or function. We went over this in 1a, but we can simplify this entire term into n squared because asymptotically they're the same. So if instead of this long term, you were to write n squared, this recurrence would also be correct because they have the same asymptotic runtime bounds. All right, now let's use the master theorem to solve this recurrence. So here's the master theorem. It's also in that cheat sheet in the last couple of pages of your section handout. But basically what it says is that if we're given a recurrence in this form, where we're doing some amount of base case work or constant base case work, and we have a constant number of recursive calls, we divide the input by a constant b for each recursive call, and we're doing additional work where we raise n by some power, and we can also multiply that by a constant. Then our recurrence is in a form where we can apply the master theorem. The most important constants to keep track of, though, are our a, our b, and our c. If we know we can apply the master theorem to a recurrence, this is all we really have to look out for once we are guaranteed to be able to use the master theorem to solve a recurrence. And once our T of n or our recurrence is in this form, then we can look at the big theta possibilities for our master theorem recurrence. And depending on if log base b of a is less than our constant c, if log base b of a is equal to our constant c, or if log base b of a is greater than our constant c, then we'll get different big theta runtimes for each case. All right, let's apply the master theorem to solve the recurrence we just found. So looking at our recurrence, the first step is always to make sure that our recurrence matches the master theorem. In this case, it does. We do a constant amount of base case work, we multiply, or we have a constant number of recursive calls, we divide the input by a constant for each recursive call, and we have a constant n squared term for the rest of the work. And then you can also say that we're multiplying this n squared term by 1. So there is a constant e. So it does match. Let's go. And then once we can verify that our recurrence matches the master theorem, the next step is to identify our a, b, and c. So looking at our recurrence, right off the bat, we see that our a is 4, our b is 2, and our c is 2. Just because we can simplify this to n squared and get the 2 from there. And these values are conveniently written down on the slide. Cool. Real quick, the way I remember the a, b, and c constants is that we just move left to right. So we're going to have our first constant a, be multiplied by the number of recursive calls. Then we have our single input inside of the recursive call, and then we divide it by our second constant b. And finally, we have our n term that's raised to some power z. So just moving left to right, I find it isn't too bad to memorize. But don't worry about always memorizing the master theorem or having the master theorem memorized, as it will be provided to you. Great. So now we have our a, b, and c values, and now we just have to compare log base b of a to our c. Log base b of a is the same thing as log base 2 of 4, which is equal to 2. And our c is equal to 2. Comparing the two values, we find that our log base b of a is equal to c, which means we're in this case. And the big theta runtime of our recursive function is going to be big omega of n to the power of c times log n. Since our c is 2, this means our recurrence is big theta of n squared log n. All right. Now let's take a moment and pause this video to attempt all the master theorem problems on your section handouts. All right, I'm assuming that you at least gave these problems a look, or you even attempted all of the master theorem problems. Now let's walk through these. For this first question, we can apply kind of our mechanical master theorem procedure, right? As a reminder of what we covered in the master theorem walkthrough, the first step is to verify. We can use or apply the master theorem, or the recurrence is in the right form to be able to use the master theorem. The next step is to identify your A, B, C constants. The third step is to compare our log base B of A to C. And our fourth step is to select the big omega from this comparison. Cool. Let's go through these steps. First, verify we can apply the master theorem. Well, for that to be the case, we need constants in the appropriate places. We do a constant amount of base case work. We have a constant number of recursive calls. We divide our input by a constant. And we have a constant order and then value raised to a constant term. And we also multiply this term by 1. So we're good. We verified we can apply the master theorem. The next step are to identify A, B, and C. Moving left to right, our A is 3, our B is 4, and our C is 2. A is equal to 3, B is equal to 4, C is equal to 2. Next up is to compare log base B of A to C. We have our C is equal to 2, so now we just need to calculate log base B of A. So log base B of A is equal to log base 4 of 3. And we don't even need to find the actual value, right? Log base 4 of 3 is less than 1, and C is equal to 2. So we know that log base 4 of 3 is less than C. And looking at the master theorem, we are in this top case, where log base B of A is less than C. Then our runtime is big omega of n to the C. So this means our T of n is big omega of n to the C, or n squared. Great. Once you do a few of these, it's very mechanical. So yeah, once you practice a few times, it's literally the same procedure over and over again, which is what's nice about these types of problems. All right, let's try to pick up the pace a little bit. Looking at this recurrence, we know that we can use the master theorem because there are constants in the right places. Scrolling up. Cool. Next step is to identify our A, B, and C. A, B, C. A is equal to 9, B is equal to 3, C is equal to 2. Next step is to compare log base B of A to C. We have our C. Log base B of A is equal to log base 3 of 9, which is equal to 2. Now we compare log base B of A to C. So 2 is equal to 2. Therefore, C is equal to log base B of A. And we were in that case before in our master theorem, where we're on that second line, and in the case where log base B of A is equal to C, then our big theta runtime is n to the C times log n. So our runtime is big theta of n to the C, which is 2 log n. Cool. For this occurrence, okay, let's verify we can use the master theorem. We do a constant amount of work. But uh-oh, we don't have a constant amount of recursive calls. Right? A needs to be a constant. A cannot be equal to a function. Therefore, we can't use the master theorem. All the constants must be constants. Oh, I'll just highlight it. Can't use it. And that's the same answer that's given here. All right, moving on to the next one. It looks like we can use the master theorem here. We have the constants in the right places. Identify A, B, and C. A is equal to 4, B is equal to 3, C is equal to 1. Now compare log base 3 of 4 to C. Log base 3 of 4 is greater than 1, so log base 3 of 4 is greater than C. Or log base B of A is greater than C. Therefore, we're in the last case of the master theorem, where the runtime of this recurrence or function is n to the log base B of A. So our runtime is big omega of n to the log base 3 of 4. And we're in exponential time. No, this is polynomial, sorry for that. Cool. Looking at this one, let's verify we can apply the master theorem. Constant, constant. Oh, interesting. So we're dividing n by 1, but now we also have this -2 term. That's kind of weird. And it turns out we actually can't apply the master theorem here. We can't have additional terms that don't simplify into a single n term that's divided by some value. Or literally just a single n divided by some value. So can't have additional terms that don't simplify. Therefore, we can't use the master theorem. Yeah, the structure of the current recurrence has to match exactly in all the areas. So that's why we can't use it here. And that's the same answer that's given via the section problem solutions. All right, let's get into some hashing. Great, let's jump into some hashing. As a reminder from lecture, hash tables are one way to implement the dictionary or map ADT, where we'll have a collection of key value pairs that may or may not be sorted by their keys. And we now have the ability to look up values given their key. This lookup features like the key component of a dictionary or a map. How do we do this? Well, we can use an underlying array where we map a key with key x to a particular array index or bucket using a hash function. And as we'll see in a little bit, the choice of our hash function is important for many reasons, such as guaranteeing an average constant lookup time. And one example of a hash function here is that we'll just map the key to the value resulting by modding the key by the size of our hash table. In this case, it's 10. So 0 mod 10, this key value pair would be mapped to 0. So that's how we ended up with foo in index 0. And if we tried to insert the key value pair of 5 bar, 5 mod 10 is equal to 5. So we would input bar into index 5. But wait, what if two of these key value pairs map to the same index? This will result in what's called a collision, right? Ideally, we'd be able to store both key value pairs that map to a single key without having to overwrite one or the other. One way to do this is by using a collision handling technique called separate chaining, where instead of directly storing the values in its corresponding array index, instead we will store linked lists at each bucket. And if two key value pairs map to the same buckets, then we will just simply append that new value that we're adding to this bucket to the end of our linked list. So this way we can store multiple values in the bucket that they were mapped to, as opposed to having to overwrite a value at that particular index by only storing a value and not a list or collection of values. And also as a reminder, whenever we're working with these hash functions and mapping a key to an index or buckets, we should be modding by the table size. So suppose we use some hash function that returned a value that was greater than our table size, and we didn't mod it. If that were the case, and this hash function returns a value greater than the largest index, which in this case it's 9, then we would receive an index out of bounds exception for trying to insert a value in an index that was higher than the greatest index in the array. In order to combat this, we just have to mod by the table size to guarantee that we're placing values inside of a valid index in our underlying array. And a note on hash function quality: the more evenly our hash function distributes keys, the faster our dictionary operations are. Why? We'll dive into this in the upcoming slides. Let's take a moment and please attempt problems 1A and 1B by yourself, and then I'll walk through it. So pause the video here and attempt those problems. All right, I'm going to assume you attempted these problems, and now let's go through the solutions. For problem 1A, we're asked to map all of these key value pairs to a hash table with an internal capacity of 10, or there are 10 buckets, with the hash function for x, right? So we'll have an array of 10 buckets. We'll use the hash function for x to generate a hash value for each key, and then we will mod that hash key by the table size in order to insert our value into the appropriate buckets. So with this first key value pair, 1A, we first hash the key. So when we pass 1 to our hash function, we'll receive a hash value of 4. And then we mod 4 by the size of our table, or 10, to get 4. So now we'll place this key value pair in the linked list at bucket 4 in our hash table. And we just repeat the same process for all of the key value pairs. We do the same thing for 4B. So when we give our hash function 4, it'll spit out 16, and we just mod 16 by our table size to insert this key value pair at the linked list 6. And we repeat this process. 2 times 8, or 4 times 2 is 8. 8 mod 10 is 8. Oh my goodness. So we will place this key value pair at bucket 8 and just do the same thing. H of 17 is 68. 68 mod 10 is 8. Anything mod 10 will just return the value in the ones place. So then we append this new key value pair to the end of the linked list at bucket 8. 12 times 4 is 48. 48 mod 10 is 8. we'll insert 12e at bucket 8. For 9e, 9 times 4 is 36, 36 mod 10 is 6. We'll insert 9e into 6, or bucket 6. All right, 19f, 19 times 4 is 76, 76 mod 10 is 6. Insert 19f in the bucket 6. Oh, but this is interesting. 4 is 6. Before, we know our hash table. What's going on to the highlighter? Okay, cool. Oh my god. Our hash table contains the key 4 already. So when we're inserting a key value pair with an already existing key into our hash table, we'll overwrite that existing key value pair's value. So our 4G will map to bucket 6. And since our key is 4, and we already found the 4 in our linked list, we simply overwrite that value of that existing key value pair to contain the new value, or G in this case, where we update the values when our hash table already contains the same key. Great. And we just repeat this process with the final result of this, where we've inserted all 1, 2, 3, 4, 5, 6, 7, 8 key value pairs into our hash table. Let's move on to problem 1b. So problem 1b gave us these following stipulations, where we had a hash table with an initial capacity of 12. We resized the hash table by doubling the capacity. We're using integer keys with the hash function for x once again. And then we had the answer, why is this choice of hash function and its initial capacity suboptimal, and how do we fix it? Well, the first step is identifying why this choice of hash function and initial capacity is suboptimal. To do this, let's try mapping a few keys to buckets. So 1 will be mapped to 4 mod 12, which is 4. 2 will be mapped to 8 mod 12, which is 8. 3 will be mapped to 12 mod 12, which is 0. 4 will be mapped to 16 mod 12, which is 4. And oh, okay, we start to see the pattern. This should be 20. And finally, 6 will be mapped to 24 mod 12, which is 0. And this pattern will continue, where all of our values are only mapped to 3 buckets. All the key value pairs will be mapped to the same 3 buckets because of our table size and our hash function all work in multiples of 4. And with the size, and by modding 12, we're guaranteed to only end up with the values 4, 8, and 0. And oh no, we're only mapping to 3 of the possible 12 buckets. That's going to result in a lot of collisions, a lot of long linked lists at these buckets, as well as decreasing the performance of our hash table. And then if we try to double the size, we would find that instead of only mapping to 3 buckets, we would then only map to 6 buckets when we double the size. So we only slightly increase the number of buckets our hash. We slightly only increase the number of buckets that we will map our key value pairs to. We still only map to 1/4 of the available indices. So how do we fix this? We could pick a new hash function that's relatively prime to 12, for example, 5x. So where 5 isn't a factor of 12. We can choose an initial table capacity that's prime. And modding by prime numbers will more spread out our keys once we hash them. And finally, we can resize differently. Once again, primes, which are really nice to work with when trying to spread out our values, by instead of doubling the table size, choosing a larger prime number that's roughly double the size. Long story short, prime numbers will almost always improve our hashing. All right, pause the video here and attempt problems 4A through C, and then I will walk through them. All right, let's go through the solution. So for the following problem, we're assuming that an int list is a list of integers. The hash code of our int list keys is the sum of the integers in the list. Int lists are only considered equal if they have the same size and the same values in the same order. And we're working with a 4-bucket hash map that only has 4 buckets, never resizes, and uses separate chaining where we add new values to the back of each bucket. For 4.1, we were asked to answer what will be returned from this function call if we were to pause on line 4. So up until this point, we created our 4-bucket hash map. We made our list 1, which contains the values 1, 2 in that order, and we put our list 1 as our key with the string dog as its value. Because the hash function is the sum of all the values in our list, a list containing 1, 2 will be mapped to index 3, mod 4, which is still 3. And then we will insert that key value pair into this bucket at the front of the linked list since there are no elements originally. And when we call gets of this list, we will hop over to bucket 3 and return the stored value dog. All right, for part 2, we then execute the line of code, list 1 to add 3, and then pause here on line 6. What will be returned from the following statements? Gets on an int list of 1, 2, and calling gets on an int list containing the values 1, 2, and 3. So for this first line, we'll look up a list containing the values 1 and 2. We'll hash this list and receive the value 3 and then mod by 4. So we'll look at bucket 3 and we'll compare the keys to try and find one that's equal to a list containing values 1 and 2. However, an int list of 1 and 2 is not equivalent to an int list containing 1, 2, or 3, which is what's contained in bucket 3. So we return null because no list containing only 1 and 2 is in bucket 3. And then when we try to get int list of 1, 2, or 3, we look at buckets 1 plus 2 plus 3 mod 4, which is equal to 2. Bucket 2 is empty, so there is no match key, and we also return null, right? Even though there's a list containing the values of 1, 2, or 3 in our hash table. And then finally, is there a problem with this code? If so, explain below. And we've seen that there is a problem, right? If we change a key while it's inside of the hash table, or a key is mutable, we would then cause it to be in the wrong buckets. And this would mess up all of our lookup and other hash table operations. So never you do this. Mutating your keys once they're inserted into a hash table will result in disaster. The mutable keys were the issue here. That's everything for this section. And yeah, have a great week, everyone.